Hi, everyone, and welcome to another episode of the Final Frontier podcast. I'm your host, Daniel Faranetta, and I have a really exciting guest for you guys today. His name is Chris Faranetta, and he is vice president and co-founder of NearStar Fusion. And today's topic is actually really incredible. We're going to go over nuclear energy, and as you guessed it by the name, nuclear fusion as well, and its space applications. So without further ado, Chris Faranetta, thank you very much for joining us. It's an absolute pleasure to have you with us today.
Thanks, Daniel. Glad to be here.
So before we jump into the topic, Chris, why don't you share with us a little bit about your background and what got you started in the space industry?
Well, I was, as a kid, I was tremendously inspired by the Apollo program and just always was interested in space, always interested in science and technology. In fact, I was very lucky in that I grew up in Princeton, New Jersey area, and we had the university, Princeton Plasma Physics there, and also RCA David Sarnoff Labs. And so I was always around the children of scientists and scientists, and we were always doing kind of sciencey things, launching rockets and stuff. And so it was a great place to grow up and develop an interest in science. You know, from there, I went to work for Gerard O'Neill, who was professor of physics emeritus at Princeton, New Jersey, and he founded the Space Studies Institute, which basically researched ways of doing large-scale habitation and utilization of non-terrestrial resources, primarily from the moon in space. And so I got involved in that in the late 1980s. And then from there, we were at the time when I joined Space Studies, they were putting together an effort to do a lunar prospector, which was a lunar orbiting probe to look for ice on the moon. And at the time, they had enough money to build the spacecraft, but not enough to launch it. I came up with the idea, again, this is the late 1980s, of using the Soviets. And that developed my relationship with the Soviet and then Russian space program. And I went to work for Rocket Space Corporation, Energia, which you may know, it builds the Soyuz and Progress vehicles for the International Space Station and pretty much runs the Russian segment, for better or worse.
Very fascinating background. And from our initial call, you also mentioned you have a mutual friend with Andy Aldrin. You say you've worked with him before. He was my professor with the Commercial Space Studies program.
Yes, and actually, I know Andy from work in the Russian space program.
Great. And so you've had some experience in the past working on some lunar missions. And what's your take on the current lunar initiatives that are happening today?
Well, I think it needs to happen, and I think it's great. It's a great jumping off point. There are plenty of resources on the moon that could be put to good use. So I'm looking forward to it. And I'm glad the Chinese are going there, because if the Chinese are going to be there or will be there, that means that hopefully we'll be there too. We, the United States, and partners.
You think that could be another lunar space race similar to what we were having?
I hope so. And and again, I see it as a jumping off point for doing things further out in the solar system and further in too.
Great. So getting to our topic, why don't you share with us a little bit about NearStar Fusion?
So last year, my boss, we spun NearStar Fusion out of another fusion company called Hyperjet Fusion, which does work for the Advanced Projects Agency for Energy, it's ARPA-E. And with those projects, we're teamed up with Los Alamos National Lab. And my boss is Doug Witherspoon, he's a co-founder. He's been developing high-performance plasma guns and rail guns since the Star Wars program in the early 1980s. And what got him interested in rail guns was impact fusion. And impact fusion is where you take a projectile and you hit a fusion fuel target of hypervelocity, and you get fusion ignition. And so they were trying to do impact fusion in the 1980s, and were not successful, but they developed some high performance rail guns, which were then used in the Star Wars program. So he's always had this core interest in fusion energy and impact fusion. And so we decided that we wanted to form a company that would focus on impact fusion last year, and we incorporated NearStar Fusion in April of this year. And NearStar Fusion is working on a new type of fusion energy, which is called hypervelocity gradient field fusion, or HGFF, and that's the working technical name for it. And how it works, how the reactor concept works, you have a very long hypervelocity plasma armature railgun, which is self-augmented. It's just a fancy way of saying that the plasma in the gun is amplified using a special process. And the gun fires basically like a soda can size fuel capsule. So imagine an aluminum can with deuterium tritium gas, and it fires it at hyper velocity about 10 kilometers a second, which is well over 10 times faster than a high-powered rifle bullet. And it fires the capsule through the center of an electromagnetic coil, and the electromagnetic coil is about the size of a car tire. The gun's about 100 feet long, and the coil is about the size of a car tire. It has very strong converging field lines, and so as the capsule passes through the coil, it's rapidly crushed, and you get ignition. And if you get a fusion, you get a little mini star in the chamber about the size of a small office, and that mini star radiates neutrons, and along the walls of the chamber is flowing molten salt, and the neutrons hit the molten salt, they slow down, they heat the molten salt up even more, then you run that through a heat exchanger, boil water, make steam, and run a turbine. And so gradient field fusion was initially developed under a NASA Innovative Advanced Concept grant. You might ask yourself, so why is NASA interested in clean energy? Well, it turns out that they kind of are, but they're really more interested in fusion spacecraft propulsion. And so this reactor concept that I just explained to you can actually be used as a fusion rocket engine in space. And it's basically a pulse system where you're firing once every few seconds. And the chambers for the propulsion system is open in the back, and you don't have a heat exchanger. You just have an explosion out the back. And so you don't even have to have energy net gain to have an efficient propulsion system. So we're very excited about that. And what's also very appealing to us is that as we develop HGFF, not only do we have an experimental reactor that we'll be developing, but we'll also be developing a fusion rocket engine test stand. And so it has this very synergistic dual use.
That's incredible. So the goal is not to sustain a fusion reaction; it's to use impulses of those reactions.
Well, it's a pulsed fusion reaction. So when you're making energy, you're firing about once a second, and you would have rows of these guns firing into a chamber, and so you figure one gun, one chamber would take you like 100 kilowatts of energy input into the gun to generate about 50 megawatts of energy out of the reaction.
That's incredible. And what were the limitations in the 80s to be able to produce a solution like this? Was it primarily materials?
Well, at the time, so in the late 70s, early 80s, they figured they had to accelerate the fuel capsule up to 200 kilometers a second, right? Which is it's hard to do 10 kilometers a second with a railgun, right? And so we figured out that if you magnetize and preheat the target, you only need about 10 kilometers a second. So there was more science that needed to be done to figure out how this make the whole thing work. And it's kind of like that's part of the problem with fusion in general, is that for the last 50 years, plasma physicists have been saying that fusion is 20 years away. And the big reason for that is that their knowledge of plasma physics was not, they almost didn't know what they didn't know. And so they would always come up against a new problem. And so, but we're on this slippery slope now where we've learned a lot in plasma physics, and also we have cheap, ubiquitous computing power, so we can do better modeling. And an example of that is the announcement that the National Ignition Facility made, which they're doing laser fusion, where they've demonstrated a certain amount of gain in their reaction. So, yeah, it's exciting. We're getting there. We're converging on the goal of more energy out than what is put in.
Net positive. That's the goal. So why hasn't nuclear energy been more widely used in space today?
Well, I think that's really coupled with the question, why hasn't space been more widely used? And it's just, I think that there really hasn't been many opportunities. Look at how long it took to get a spacecraft electric propulsion as a primary propulsion system on a spacecraft. It took decades, and it was really, I guess, getting mission, and arguably there are a fair amount of nuclear-powered spacecraft and rovers out there that are still working, and using radioisotope thermal generators. And the Voyagers are probably the best example. God, when the Voyagers were launched, it was like 1975. I think I was in like 6th grade or something, or no, I was in 7th grade when they were launched. And they're still going, and so it's an amazing thing. And it's really a testament to why we need nuclear fission and we need nuclear fusion in space.
That leads to the next question. What's the benefits of utilizing fusion versus fission? What are those differences?
Well, okay, the key difference is this. With hydrogen and oxygen, liquid hydrogen, liquid oxygen, you get an ISP of about 450 seconds. With nuclear fission, nuclear thermal propulsion, you get an ISP of 900 to 1,000 seconds, around in there. Starting out, it's going to be around 900, which is good. That's a nice performance enhancement over chemical. With fusion, your ISP is 30,000 seconds to 50,000 seconds. Wow. So that's roughly. So let's say when Earth is in its closest orbit to Mars, it takes you what, about 7 months to get there. With fusion, you could leave anytime. It'll take you about 90 days.
Wow.
So I mean that spells it out. So, but that said, now like with our system, with our reactor concept, which would be a very large spaceship, we need nuclear fission. We need a small fission reactor. We call it we need a car battery. So because if we shut down the reaction of the fusion reaction, we need a source of electricity to charge the banks in the railgun. So yeah, fission and fusion are actually extremely synergistic in the future of space travel and space power. The folks at Los Alamos, they've come up with a great system, Kilopower, which is a 10 kilowatt fission reactor that's extremely safe and reliable to launch. And, boy, it would be great if we had like 5 of those on our spacecraft to jumpstart our fusion reaction. When we get into orbit and we need to shut down the fusion rocket engine, we've got those fission reactors there that we can rely on for power and to start, crank the fusion engine. So it's extremely synergistic. It's not an either or situation. It's one built on the shoulders of the other.
That's incredible. And you've touched on this quite a bit already, talking about the rovers utilizing nuclear energy to keep power. And what other applications does nuclear energy have in space?
Well, look, we're going to need, if we're going to have a lasting, continuous presence, a viable moon base. There's a 2-week long night on the moon, so you want to have kilopower there powering those moon bases. And yeah, because solar is great when the sun is out on the surface. I guess you could actually maybe beam power down, and so there are different things that you can do. But yeah, I mean, just look at how much nuclear power has transformed submarines. It used to be that they could run underwater until the batteries ran out. Then they'd have to surface and run their diesel engines. And with nuclear power, you don't have to surface, and you can crack the oxygen you need right out of the seawater. You've got that much power. And so it's the same situation with bases on the moon or bases on the Mars. You want to have the fire that's always there, which is fission, for example, and eventually fusion.
And is fusion cleaner than fission?
Yeah, it's a reaction. It's a nuclear reaction that doesn't want to happen, whereas fission really wants to happen. So much so that if you got a lousy reactor design or you're careless, you can lose control of it. But if your fission reactor breaks, the whole process shuts down. And so if you're using the easiest fuel to get a fusion reaction with is deuterium and tritium. Tritium is mildly radioactive, and so when you're running tritium, you eventually activate components in the reactor which are mildly radioactive, and you need to set them aside for about 20 or 30 years, and then you can recycle them, and so it's very, very safe, easy to handle. Basically you put them in a warehouse, and because it's very, very low level radioactivity. Whereas a spent fuel rod, if you don't a fission fuel rod, if you don't recycle it, it's dangerous for hundreds of thousands of years. And so it really comes down to having a good fission reactor design and then also having a good fusion reactor design. So I remember I said that it's the first order fuel, the easiest fuel to get going is deuterium and tritium. Tritium is made in the reactor. It's bred in the reactor by bombarding lithium-7 with neutrons, and that's how you get tritium. It's a very short-lived radioactive material. Deuterium is found in seawater, and so we've got like a million-year supply on this planet. With our approach, I neglected to mention. So we have growth potential in that we have performance growth potential. We can use advanced aneutronic fusion fuel, so we can grow the reactor performance to burn p-boron-11, and that's literally where you have a solid fuel capsule of p-boron-11 and you're firing it into a special vessel, which causes ignition, but you're doing it about 20 kilometers a second. So remember, we're going to start out firing fuel capsules at about 10 kilometers a second, and then hopefully, we'll be able to go to the turbo. We're going to start out with the Model T, and then we're going to work our way up to the Turbo Carrera or Tesla Model S, with our reactor performance. And and what's neat is that the reactors are modular, and so we can modify a DT reactor to then burn P-borne 11 fuel.
Has there been big initiatives from government as well as private to make fusion, more readily available?
Yes, in fact, so I've been working in trying to commercialize fusion energy, which has been a very long slog since 2008. And, we couldn't have done it without the support of the Department of Energy and ARPA-E. And, there were times when, the money just dried up. And it was so funny because you'd go and talk to a venture capitalist and they were like, you want to do what, and they just didn't, they never would return your phone calls. And but now private money is coming in, and and again, we still need a synergistic approach of both government and non-dilutive government funding and private sector money, and it's starting to happen. There's a variety of companies, about a dozen private companies working on both fusion energy and about 4 companies working on fusion propulsion in the United States, gradually moving that along. Right now, it's at a very low technical readiness level, the propulsion side, but the energy side is much further along.
Wow, that's incredible. And in terms of capital necessity, I know traditional nuclear generators, could cost hundreds of millions of dollars to produce. Is there a difference? Is it cheaper? Is it more expensive? Creating a
we're going to get to a commercial scale design for a terrestrial fusion reactor, right? We're going to need hundreds of millions of dollars to do that. And it's going to take us about 10 years, we hope, right? But think about what you achieve. When I say that's a design that you can then mass produce. And you basically, you solve the clean energy problem for the entire planet pretty much for forever. And so that's a really, really wonderful goal. And think about it in terms of it's a power system for our spaceship Earth, and we need to really start thinking in terms of Earth as a spaceship that's in orbit around the sun, and because we've got to practice. My point being is that we need better stewardship of the planet and its life support systems. You wouldn't treat a spacecraft this way, or a space station this way, or a base on the moon. You wouldn't not bother to change the air filters or not maintain the life support system, and so there's kind of this awakening going on right now. And again, it's really interesting. It's fascinating that it's completely synergistic. If we're successful in terrestrial energy, fusion energy, we literally then have the keys to the whole solar system. It becomes a huge enabler in traveling throughout the solar system.
So who from the audience that's listening or watching would you like to reach out to you?
I really anyone who's interested. It's an exciting area. I mean, when you look at the mission that you can do with fusion propulsion, like my favorite is going out to the gravitational lensing point in orbit around the sun, where we look back and you can use the sun as a gravitational lens, and then you'll be able to look at, extrasolar planets and see if they're like cities, or, you see the atmosphere of that extrasolar planet. And, it just becomes a huge enabler for doing these missions. It puts them within human time scale. And then you're going out to the asteroid belt, bringing back material, going out to the moons of Jupiter or Saturn and bringing back maybe marine life from those planets. Just really, really neat missions. Mars, to me, Mars is boring, right? We could do better than Mars. I mean, wouldn't it be cool if you brought back a fish from one of the moons, the outer solar system? I mean, we know there's liquid oceans under, under the ice of these moons and stuff. So there might be marine life.
That'd be incredible. And many people argue, especially, and I understand these arguments, but don't necessarily agree with them, that people are spending billions in space, and we got problems here on Earth. But you're a perfect example of investing in additional capabilities. Could solve a lot of those problems. Ask you that question, how would you answer?
Daniel, it's so funny because we get that with we get people here on Earth who say, you want to spend billions of dollars in developing fusion? If you electrify, so look at the market right now. So right now, the Earth spends, or human civilization spends $6 trillion annually on electricity, right? And if we electrify heavy industry and transportation, it'll be an annual expenditure of about $12 trillion. And you're complaining to me about, spending billions of dollars? I mean, how can you afford? It's like, how can you afford to do it? It's like, the question is, how can you afford not to? I mean, it's a huge opportunity. It's so funny. We're part of, NearStar Fusion and Hyperjet Fusion, our other company, we're part of the Fusion Industry Association. And it occurred to me the other day, we help each other. We get together and we help each other with our problems, and we're working to try and get funding from the government. And I'm thinking, we're really, really collaborative with one another. And then it occurred to me, well, yeah, we should be, because we're carving up a multi-trillion-dollar pie. There's plenty of pie for everybody. Yeah. So there's nothing to argue about.
Well, Chris, it was great having you on the show. You did a fantastic job, and you shared a wealth of knowledge with us, and really a fascinating topic. And thank you for taking the initiative to provide clean energy for the world. Chris, it was an absolute pleasure. Thank you for joining us.
Yeah, my pleasure. Yeah, it's lots of fun. It's great fun talking to you.
All right, everyone, that was another show of the Final Frontier podcast. If you liked it, if you enjoyed it, please hit the like on YouTube. Follow us on the different podcast platforms that we're on. We're on Spotify, Apple Podcasts, Google Podcasts, Pandora, literally everywhere. Give us a follow, give us some support. And if you want to watch past episodes, you can also visit us on our website, thefinalfrontierpodcast.com. Thanks, and I hope to see you guys in the next one. Bye-bye.